So we know that 1 over 1 minus x, right, is our power series, 1 plus x squared, and so on to x to the n. Right, we talked about that yesterday, and we talked about that it converges for -1 to 1 because it's just a geometric series and the common ratio is x, and so absolute value of x is less than 1. That all makes sense? Remember all that from yesterday? I hope.
Yes.
All right, cool. So what we want to do then is we want to see if we can come up with a series, a power series, to represent 1 over 1 minus x to the second power. Any thoughts on how we might go about doing that? Okay, so the denominator is already factored, Darius. But okay, we can think about distributing it out, which would give us 1 minus 2x plus x squared in the denominator. And if we look at that, that doesn't really look like, no, it doesn't really look like a real nice, simple, easy function. We could try to rewrite it out as 1 minus the function 2x minus x squared, right? Yeah, so that's what I was just, well, it would have to be a minus, Aiden. So we could write it like this: 1 over 1 minus 2x minus x squared. And the problem that we have here is there's not a problem per se, but we could rewrite this then as a sum of 2x minus x squared to the n power, right? A sum from n equals 0 to infinity. What would the radius of convergence then be for this? We'd have to have the absolute value of 2x minus x squared has to be less than 1, right, which would tell us that 2x minus x squared would be between 1 and -1. And then this becomes maybe not the easiest inequality to solve, right? It's not horrible, but we'd have x, we'd have 2x minus x squared minus 1 would have to be less than 0, and we'd have 2x minus x squared plus 1 would have to be greater than 0. And that's going to give us multiple weird little sections of this that are going to sort of not be similar to this interval that we started on. So what we want to try to do is see if we can find a way to make a series representation of this, a power series representation of it that's still valid on this same interval. Maybe I should have said that from the start. I didn't say that from the start, but I want it to be valid on that same interval. And so this method, while it does give us a series that would work on some interval, it's not necessarily valid on this same interval. Because a lot of the time what we want to do with our series is evaluate them at very small numbers between -1 and 1, because those are the numbers for which most of them converge, and generally what we want to work with our series, generally. So does anybody else see any other relationship between these two functions? So Let me see. Lots of you have said things here. 1's the square. Okay, yeah. So the bottom one is the square of the other. That's true. Okay, that's true. It's self multiplied by itself. Those are all true things. I agree. But that doesn't necessarily mean that. I mean, that would mean that we would have to square this whole series. And it's really hard if we have an infinite number of terms to FOIL, per se, to FOIL them out, right? To multiply a 1 by the 1, and then a 1 by the x, and a 1 by the x squared, and 1 by the x cubed, and a 1 by the x to the, 4th and 5th to the n, and then the x by the x, and the x by the x squared, and the x by the x cubed. We might try to do that. If we did that, let's think about that. The 1 times the 1 would give us a 1, and the 1 times the x would give us an x, and the 1 times the x squared would give us an x squared and an x cubed, right? And we'd end up with the same series again, but then when we did the x, we'd have x times the x, which would give us, we have an x times the 1 first off, which would give us what? Another x. And then we'd have the x times the x, which would give us an x squared. And then we'd have the x times the x squared, which would give us an x cubed, and so on. And then the next one, when we multiplied the x squared through everything, the x squared would get multiplied by the 1 to give us an x squared and an x cubed, and so on. And so if we were to add this all together, what would our series end up looking like? It'd end up looking like 1 plus 2x plus 3x squared plus, and we'd have another one here, and so on going down. It's cubed. Plus 4x cubed, and then 5x to the 4th. And what might we note here then, potentially? With any luck. Yeah, it ends up looking like nx to the n minus 1, and that should look very familiar to you, right? What is nx to the n minus 1? Should look really familiar. What's nx to the n minus 1 with relation to x to the n? Right, it's the derivative of x to the n. You all agree with that there?
Yes.
Okay, so if we took the derivative of 1 over 1 minus x, what do you get? Using the reciprocal rule, that should be the denominator squared, right? And then times the negative, and then times the derivative of the denominator, which is this. That was the relationship I was originally hoping you guys would see, was that the second one there is the derivative of the first one. And so this is something that we can do with the power series. If I am given 1 over 1 minus x, I can take its derivative and then take the derivative of the series. So since the derivative of 1 over 1 minus x is 1 over 1 minus x squared, the derivative of the series, the sum from n equals 0 to infinity of x to the n, should be this new series that we've now got. And what we end up with is a sum from n equals 1 to infinity of n x to the n minus 1. And we have to move our index up from n equals 0 to n equals 1 when we take this derivative, because we're going from x to the n to x to the n minus 1. If we start at 0, that's going to give us x to the negative 1, which doesn't work, doesn't make any sense. But this series, you'll note, represents this series, which was just a term-by-term differentiation of this series, right? The 1 goes away and becomes 0. The x becomes 1. The x squared becomes 2x. The x cubed is 3x squared. The fourth is 4x cubed, and so on. And so we can create a new power series for the derivative of any function that will still be valid or still converge on the same interval as the original one by simply taking its derivative. Everybody see that? Any questions on that? That's a little bit of a mess up there on that page now because we did a bunch of work that I was not intending to do all of, but good or no? Okay, and so like I said, you can do a term-by-term differentiation of this power series, and so this is just the general form of it, and if we take the derivative of it, we end up with something that looks like this. And so if the original one converges, remember for x minus a, absolute value of x minus a is less than r, and that tells us that the new one will also converge for the exact same values. Because what we're not doing is we're not changing this r value, right? Our r value is staying the same. We may be throwing some extra constants out in front of it, and we're maybe dropping this power by 1, but we're not changing the common ratio between the terms. Exactly, Nick. That's what we did. We took the derivative of this power series. So we took the derivative of the power series, right? And this was a constant times x minus a to the n, right? So it was the constant times n times x minus a to the n minus 1. And each term, we just term by term differentiate and move the index up from n equals 0 to n equals 1. And that should work for any power series that you've got. You can find the power series to represent its derivative by just simply taking the derivative. Good or no? Any questions on that? We're going to do a fair amount more with this on Monday, but that's our basic introduction to it.